Good morning, dear student friends. I'm Professor Satyavan Jagdali. Today we are going to discuss about the impact of the jet that is related to the or most applicable for the turbines and the pumps, which includes the various aspects of the things. I have completed my MTech Civil in Hydraulic Engineering, and right now I'm pursuing my PhD in Civil Engineering. I am working with Sveris College of Engineering, Pandharpur, Maharashtra. The content will go for firstly we are going to study about the velocity triangles at the inlet and outlet for the moving vane where it is striking. It is struck by a jet tangentially at its one of the tip or one of the end and leaving from the another end. This is the first part. Second part, we are going to find out the force exerted by a jet on the moving vane. It is acting on the tangentially at its one of the end and leaving from the other end. And the next part, that is a force exerted by a jet on series of radial curved vanes. Those are mounted on the wheels. As I have explained earlier, that is this part is most essential in the further studies of turbines and the pumps. So firstly we will go for the velocity triangles. So consider this is an schematic diagram which is shown over here. In this we are finding as this is a one of the vane, curved vane, which is moving towards the right hand side. This is the axis which we are going to consider as axis of the vane, and we are going to assume this axis as a x-axis. So the perpendicular to it will be the y-axis. So this is nothing but the y-axis and this will be our x-axis. Let us have a tangents to the outlet tip. This is the outlet tip and this is the inlet tip. So we had a tangent to this inlet tip and outlet tip, and we're going to assume that the angles made by them with respect to the horizontal as a theta for the tangent of inlet tip and the phi for the outlet tip. The further assumptions which we are going to have, those we will discuss firstly. Let us assume that the different parameters, those are essentially required to be in the derivation in the further understanding. V1, that is the velocity of the jet at the inlet of the vane. This is the jet. We are going to assume that it is going to strike the vane at this point, that is the inlet point. Suppose that this point is a B and this is the point A. So the velocity of the jet directing along the AB is nothing but the velocity of the jet which is striking at the inlet of the vane. So we are assuming that this is the inlet tip of the vane and this is the outlet tip of the vane. Similarly, we are going to assume that the V2 as the velocity of the jet which is coming out of the tip of the vane, that is from the another tip we can say. So the velocity with which the jet is leaving the vane, that is the V2 which you have shown here. In next parameter, we are going to assume that U1 and U2. So U1 and U2 are nothing but the tangential or the peripheral velocities. So U1 is the tangential velocity or the linear velocity of the vane at the inlet tip, that is towards the right hand side. So along this direction, this is the U1, and along this direction at the outlet tip towards the right hand side is a U2. Next parameter, we are going to assume that is regarding the angles, that is alpha and beta, what they are therein. So alpha, we are going to assume that the angle made by the velocity V1 or the jet we can say at the inlet tip, or the velocity V1 of the jet with respect to the horizontal. So this is the horizontal line once again parallel to our x-axis, and angle made by the jet with respect to horizontal as alpha. There is the velocity V1 of the jet making an angle alpha with respect to the horizontal, whereas the beta is the angle of the velocity V2, that is the velocity of the jet leaving the tip with respect to horizontal as a beta. So this is about the alpha and beta. The next angles we are going to assume that is the theta and phi. So we'll discuss that what is the theta and what is the phi. So theta is the angle which we have already discussed, that is the theta angle of the tangent drawn at the inlet tip, and the phi is the tangent drawn at the outlet tip. But here when the jet is going to strike to the vane at inlet tip, or when it is going to leave from the outlet tip it is not going to strike exactly with a velocity v1, that is the velocity of the jet. It means that as the plate is moving towards the right hand side, so the jet at the time of the striking the plate at this end will not strike at the velocity v1, but it will strike at a relative velocity, which is the relative velocity of a jet with respect to the plate. It means that the component of the velocity v1 along the tangential or along the x direction minus the tangential velocity of the plate towards the right hand side at the inlet, we can say, and that velocity we are going to assume as a relative velocity vr1 at the inlet tip. It means that the magnitude of the relative velocity is nothing but the component of the velocity of the jet at inlet along the x-axis. So this will be the component along the x-axis minus the tangential velocity of the plate, that is u1. So here we are getting a triangle, we can say. How the triangle is getting formed here? In A is the point from which the jet has been issued, and B is the point, that is the inlet tip of the vane, and AB represents the velocity of the jet in magnitude and direction. So direction we had assumed that alpha with respect to the horizontal. So if you will extend the point A further along the x-axis and representing the velocity, that is a linear velocity of the vane at the inlet tip as a u1, then AC represents in magnitude and direction the tangential velocity of the plate at the inlet end. So by law of a triangle or force triangle, we can say, so the you will go for the addition of the u1 and a vr1, we will have the v1 here. So, or in other terms, we can say that the vr1 will be equals to the v1 minus u1, that is by the law of triangle of forces, we can say. So now you will extend this term. What term we are talking about? You will extend this linear velocity u1 further towards the right hand side up to the point B, and you will drop the perpendicular from the point B on a line extended from the AC, that is extended up to the point D, that is intersection of the perpendicular from the B and extension of the AC, that is a point D. Then in that case we will find that the A to the D is going to represent the some velocity, and that velocity is nothing but the velocity of the whirl, that is the magnitude of the velocity of the water molecules or the particles of the jet. Here we are going to assume that jet is the water jet. So the while moving the water from inlet tip to the outlet tip, it is going to glide over the surface. So while gliding the surface, it will rotate towards about its own axis, and it will rotate about the others particles too. So that velocity of the whirl is going to be represented in magnitude and direction by the AD, we can say. So AD is going to represent the velocity of the whirl. So why we have assumed that angle theta here for the velocity, a relative velocity, it is actual velocity with which it is going to strike, because when there is no friction or there is no loss of a head while movement of the jet from the inlet tip to the outlet tip, in that case the compulsorily the velocity with which that jet is going to strike, it must be tangential, that is it is going to direct along the tangent which we have drawn here at the inlet tip. It means that whatever the angle that tangent had with respect to the horizontal, that angle must be carried over here, it is the theta. So the next part which we are discussing about the velocity triangle at the inlet, that is which parameter that BD is going to represent. So already I told that if this is the x-axis, this will perpendicular axis will be the y-axis, and if you will consider here in the net direction of the flow, in that case the net direction of the flow is moving in the upward direction, as vane is curved but it is moving in a upward direction. So the net velocity or the velocity of the flow is upward, so that B to the D represents the velocity of a flow at the inlet tip, that is Vf1, we can say. So this ABD represents the velocity triangle at the inlet, which is the combination of the combination of the velocity of the jet v1, which is represented by a AB in magnitude and direction, and direction is having the alpha with respect to the horizontal. Then we have extended from A towards the along the x-axis, and we have represented the velocity u1, that is a tangential velocity in a magnitude and a direction towards the horizontal. It's a magnitude up to the point C. Then by property or by the force law of a triangle, this B to the C is going to be a exact velocity with which jet is striking the plate. That is the relative velocity of the jet with respect to the plate. So this is the VR1. Then the velocity of the whirl, we have just extended the point line AC up to the point below the point B, that is inlet tip, and we have given name it as a D. So AD is representing the velocity of the whirl, that is the whirl is nothing but the velocity of whirl is nothing but the while moving the particles of the water from point B to the point B dash, that is outlet tip, they are going to glide over the surface, and while gliding the same, they are going to rotate about themselves and they are going to rotate about the others too. It means that they are going to have the whirl action, and that whirl velocity is along the AD. And the velocity of the flow, net velocity of the flow is in upward direction. So D to the B represents the velocity of flow in a magnitude and a direction. This is all about the velocity triangle which has been formed at the inlet tip, that is point that is at the point B, we can say. Now we'll discuss the next part, that is the remaining part, we can say. Here we have not explained, that is pi. So pi is nothing but, here we will consider now at the outlet tip. So outlet tip is the point B dash. Now here the pi, we have assumed that the angle of a tangent at outlet tip with respect to the horizontal. Now as we have assumed that the plate is a smooth, it means that there is no loss of a head due to the friction. It means that when the jet is going to come out of the end B, it is going to be at a velocity, relative velocity of the jet and the plate. So plate is moving towards the right hand side, jet is moving out of it. So when it will move or when it will come out of that relative velocity, there is actual velocity, it will be exactly along, or it will be directed along the tangent which we have drawn at the outlet tip. So this along this tangent, this is going to be a velocity, that is a relative velocity with which that water particles or the jet is going to be come out of the same. So from the B dash to the C, you will have the magnitude, then direction is a pi, then B dash to the C dash represents the relative velocity of the flow. Then if this is the relative velocity, then the actual velocity of the jet, that is a V2, it will be less than the relative velocity here, isn't it? Because it will be the relative velocity will be the combination of the velocity of the jet and the tangential velocity of the plate, as here the jet is coming out in the opposite direction in which it was coming inside the plate. So the relative velocity here will be the combination of the tangential velocity of the plate, that is a u2 at the outlet and the v1 at the inlet. So we will assume that, or this will be the combination. So now you will have the tangential velocity u2, that is a magnitude we are knowing, then the tangential velocity along directed along the x-axis towards the right hand side. This is the direction, we can say. You will represent or extend the c dash further along the x-axis to the right hand side. Then u2 will be up to the a dash, that is c dash to the a dash. We are assuming that it's a magnitude and directions to the right hand side. So the c dash to the a dash is represented by the tangential velocity u2. Then if we join the b dash to the a dash, then we will get the actual velocity of the jet, that is the v2, we can say. And the angle made by the v2 with respect to the horizontal is nothing but the beta, and the remaining part, that is from a dash to the d dash, will be the velocity of the whirl at the outlet tip. Okay, and if we will drop a perpendicular from the d dash to the point B dash, then it is going to represent the velocity of the flow, that is a Vf2 at the outlet tip. So this is nothing but the outlet velocity triangle, which is the combination of the relative velocity at the outlet, which is the combination of or the resultant velocity of the tangential velocity of the plate at the outlet and the velocity of the flow at the outlet, that is a V2 and a U2, that is a combination. You will get a VR2, we can say. Then Vw2, that is the velocity of the whirl at the outlet, and the Vf2. So a triangle C dash D dash B dash represents the outlet velocity triangle for the vane, which is curved in nature and it is struck upon by a jet at its one of the end. So this is the part. Then what does it exactly means of the velocity of the whirl? That is nothing but the tangential component of the velocity V1. So this is Vw1, this is the right angle triangle, it is ADB. Then the component of the VR1 along the x-axis, that is AD, that is a cos component, we can say. This is nothing but the velocity of the whirl at the inlet, Vw1, that is a V1 cos alpha. Similarly, Vw2 is nothing but the tangential component of the V2 at the outlet, and it is nothing but the V2 cos of the beta. Okay, so this is about the velocity triangles. Here we are finding that in enlarged view, we can say. So the assumptions we had those there in moving to the right hand side. This is a tangent at the outlet, tangent at inlet. This is the inlet velocity triangle, and this is the outlet velocity triangle. So this is all about the velocity triangles at the inlet and outlet when the curved plate moving towards the right hand side, or whatever you mean with the side, right hand side, left hand side, upward, downward, etc., etc. It is struck upon by the jet at its one of the end. Okay, so now we will discuss the next part, that is a force exerted by the jet on the moving vane. That is the force exerted by a jet on a moving vane when it strikes tangentially at its one of the tip of the vane and leaving from the another tip. As it is striking therein, there is a change in momentum. So by linear impulse momentum principle we will go for, that is force into time is equals to change in momentum. So the force here we are assuming that is along the x-axis, that is the axis of the vane. So Fx is equals to initial momentum minus final momentum upon time, as I had taken this time from the left hand side to the right hand side, so it will be in the denominator. So further rearranging the same, so momentum is nothing but the product of mass into velocity. So mass into initial velocity minus mass into final velocity. Mass will be the same one as there is no leakage. So taking mass out of the same, so we will have the formulae as like mass of the water striking the vane per second into the initial velocity with which the jet strikes in the direction of motion of the vane minus the final velocity, that is with which it is coming out of the jet. So putting the magnitudes as the mass we are converting in terms of the density and the volume, as the density is a mass upon volume, so mass is a density into volume per second into the initial velocity with which the jet strikes in the direction of the motion of the vane, that is the component of the relative velocity, as it is striking with the relative velocity. So we want to have the force in the x direction, so we will be required to have the component of the relative velocity along the x-axis. So Vr1 cos theta minus the final velocity. So final velocity, as the jet is leaving the plate in the opposite sense, opposite direction, that of the direction with which it is striking the plate, so that is a negative, that is towards the left hand side. So minus of minus Vr2 cos phi. So Vr2 cos phi is nothing but the component of the relative velocity at the outlet tip, and the phi is the angle made by the relative velocity with respect to the horizontal. So Vr1 cos theta minus of minus Vr2 cos phi. So again rearranging the terms, now volume per second is nothing but the discharge, and discharge is nothing but the area into velocity. So velocity will be the velocity, actual velocity with which the jet is striking, that is the relative velocity at the inlet, that is a VR1. A will be the area of the jet. So we will get the equation density into area into VR1 into VR1 cos theta minus of minus VR2 cos phi. So after, but as we are knowing that VR1 cos theta and VR2 cos phi. So VR1 cos theta is nothing but the VW minus E1. We will see that how is it so. So VR1, the component of the VR1 along the x-axis we want to go for. So component of that velocity, that is a relative velocity along the x-axis, is nothing but the combination of the magnitudes of the velocities at the inlet, that is the u1 and the u2 we can say. So here we are finding that. So this is the velocity triangle. Herein we had a component of the VR1 along the x-axis, that is the VR1. Here this is the VR1 and it's a component along the x-axis, that is the VR1 cos theta, that is this is the CD. So CD is nothing but the combination of AC plus CD. So we can say CD is nothing but the AD minus AC. So AD is nothing but the VW1 and AC is nothing but the U1. So CD, that is a VR1 cos theta, is nothing but VW1 minus U1. Similarly, the component of the VR2 along the x-axis is nothing but the VR2 cos phi. So VR2 cos phi is from the C dash to the D dash. It is combination of a C dash A dash and A dash D dash. C dash A dash is the tangential velocity u2 and A dash D dash is the VW2. So C dash D dash, that is the VR2 cos phi, is a u2 plus VW2 we can say. So by putting those things in our equation, we are rearranging the terms and we will get the next parameters we can say here. So the next parameters we will find by rearranging the terms. Just take a so those are the terms we were rearranging for, that is components of the relative velocities. So those components now we are putting over here in, there is the VR1 cos theta is a VW1 minus U1 and VR2 cos phi as a U2 plus VW2. So by rearranging the terms we will get now Fx is equals to density into area into VR1, that is the relative velocity 1 at the inlet tip, into VW1 minus U1 representing the VR1 cos theta, this term I have quoted herein, minus of minus VR2 cos phi, that is U2 plus VW2. So now but as we have assumed that there is a no loss of the head and there is a no friction, and if you assume that initial velocity u1, the tangential velocity u1 at the inlet tip and tangential velocity u2 at the outlet tip are the same one, there is u1 is equals to u2. In that case, by rearranging the terms, the u1 and u2 will be get cancelled, because this is a minus u1, this is a minus of minus, it will be plus. So minus u1 plus u1, that will get cancelled and we will have the terms only VW1 plus VW2. But this is applicable only for the beta as an acute angle. So if the beta is a 90 degree, that beta is a 90 degree, in that case we will have for VW2 as a 0, for beta as a 90 degree. So if beta is 90 degree, VW2 will be 0. In that case, we will get the force Fx is equals to only the product of density, area, velocity, relative velocity at the inlet tip and the velocity of the whirl at the inlet tip. Now what happens if the beta is to be a obtuse angle? If the beta is obtuse angle, in that case Vw2 will be in the negative, it will be towards the right hand side, that is, and indirectly it will be a -1. So it is Vw1 minus Vw2. Thus in general we can say that the apex is given as rho A Vr1 into Vw1 plus minus Vw2, that is for acute angle and for obtuse angle. So whenever, as per the conditions of the angles, we have to consider either positive or negative. Now we'll discuss the next part, that is a work done per second by a jet on the vane. That means when the jet is going to strike the vane, then how much work it will do per second. So as we are knowing that the work done is nothing but the product of the force into the velocity. So force will be the apex, that is a tangential force we have already done, and the velocity will be the tangential velocity, that is the velocity of the plate. Why plate? Because work is going to done by the jet on the plate. It means that the plate is going to displace due to the actuation of the jet on it. So we have to consider the tangential velocity of the plate, that is apex into u, we can say. Just put up the magnitudes. So that is a rho A Vr1 into Vw1 plus minus Vw2 into u. So this is the work done per second by the jet, we can say. Now work done per second per unit weight of a fluid striking a vane. It means that we have to just divide the same by the weight of the fluid, that is work done per second by jet divided by weight of a fluid striking the vane per second. So weight is nothing but the mass into gravity. So mass again in terms of the density as a density into volume, that is a per second. So volume per second is a discharge, again discharge is area into velocity. So velocity will be the relative velocity with which it is striking. So density into area into relative velocity, it indicates the mass, and g indicates the acceleration due to gravity. Rearranging the terms, that is the cancelling the common terms, that is the rho A Vr1 will get cancels herein, and we will get the work done per second per unit weight of the fluid striking the vane as a Vw1 plus minus Vw2 into u by a g. So this is the expression for the work done per second per unit weight of a fluid striking a vane. Now we'll discuss the next part, that is a force exerted by a jet on a series of radial curved vanes mounted on a wheel. This is a totally practical application for the turbines, and the turbines where the blades or the vanes are mounted radially on its runner, and for the pumps the blades or the vanes are mounted on the impeller. So we'll discuss that. Firstly we'll discuss that how the mechanism is like this. So the mechanism is like this one. So we are going to assume that this is a wheel which is rotating about the center, that is the center of a wheel. It may happens that those vanes are extending from this tip up to this tip, that is up to the center to this one. This is for the impeller, we can say, that is a impeller of the pump, centrifugal pumps. So it extends up to this, and there will be the center of the eye center, that is center of the impeller, that is eye we used to talk about. So up to this one we can say this is the diameter. Then rather in general we can say from center to up to this. So vanes will be extending herein. So we have considered the number of the vanes mounted over the plates at the 3 as an for the understanding purpose only. We are assuming that this is a center of rotation and it is rotating with an angular velocity omega about the center. So the outer periphery, that is here for the turbines, this will be the inner portion and this will be the outer portion, and for the pumps, centrifugal pumps, this will be the inner portion, this will be the outer portion. So we will firstly discuss about the in terms of the turbines. So for the turbines, the jet is going to strike on the vanes, that is from this end. So this will be the inlet end and this will be the outlet end. So we are going to assume that here this is the inlet tip and this is the outlet tip. So this will be outlet velocity triangle and this will be the inlet velocity triangle. So with respect to that, R1 is representing the radius of the wheel for the outer periphery, that is a radius of the outer periphery, and R2 is the radius of the inner periphery of the wheel. Then we have drawn the tangents at the inlet and outlet tips. So this is the tangent at the point B dash, that is the outlet tip, and this is the tangent at the inlet tip, that is the point B, we can say. And with respect to that, with respect to those tangents, we have drawn the velocity triangle. So the V1 is the velocity with which the jet has been issued by the water has been issued by the jet. Then U1 is the tangential velocity of the plate at its inlet point, that is a B. So in magnitude and direction, we have represented AB is representing the velocity of the jet. In magnitude and direction, AC is representing the velocity, tangential velocity of the tip at the inlet. So the actual velocity with which it is going to strike the plate, that is the actual velocity of the jet with which it is striking the plate, that is the relative velocity of the jet with respect to the plate. It will be represented in magnitude and direction by the CB, that is by the force law of a triangle. And the remaining part, that is the velocity of the flow, will be along the BD, and the velocity of the whirl will be along the AD, that is for the inlet velocity triangle. Similarly, for the outlet velocity triangle, when the jet is going to come out of the vane, then the actual velocity will be the relative velocity of the jet, that will be the combination of the velocity of the jet, that is a V2 coming out of the same, and the tangential velocity of the plate at the point B. So this is going to be a VR2. Then it will represent the VR2 in magnitude and direction. Direction is the pi, we have assumed in the previous slide only. That is a B dash, C dash is going to represent the VR2. Then U2, that is the tangential velocity of the plate at the outlet, will be represented in magnitude and direction. Direction will be along the tangential direction, that is along the x-axis, we can say. So C dash, A dash is the U2, then the V2 will be the A dash to the B dash. The part A dash to the D dash is going to represent the velocity of the whirl at outlet, and a B dash to the D will be the velocity of the flow. So those are the things related to the inlet and outlet velocity triangles. Now here the force will be the tangential force, and due to that tangential force acting at the inlet tip, it will have the rotation in a anti-clockwise direction, that is the angular rotation, we can say, angular velocity, we can say, that is omega. It means that the force is nothing but the torque here, which is product of tangential force F into the radius R, and that force will be at both the ends, that is this end and this end, and combination of that is going to have a resultant angular velocity. So now we'll discuss one by one. Let's have an assumptions firstly, which we are going to have, that is R1 is the radius of a wheel at outlet vane, which we had already discussed. R2 is the radius of the wheel at the outlet vanes. U1 is the tangential velocity of the wheel at the inlet, that is the U1 herein, and we are knowing that the tangential velocity is the product of the radius and the angular velocity omega. So omega will be angular velocity, and here we have assumed that radius as R1, this has the radius R1, so tangential velocity U1 will be R1 omega or omega R1, we can say. Similarly, U2 will be the tangential or the peripheral velocity of a wheel at outlet, and that will be R2 times omega. Then alpha and beta, those are the angles of the jet with respect to the horizontal at the inlet and outlet respectively. So this is the alpha here. So this is the alpha and this is the beta. Similarly, theta and phi. Theta is the angle of relative velocity at the inlet, and the phi is the angle of relative velocity with respect to the horizontal at the outlet. Then those are also the angle of the tip, that is tangents. If you are going to have, then we will have the same angles. Then again, the VW1 will be the component of the tangential velocity at the inlet tip, as we have explained in a previous slide, that is the if you will have the component of V1 along the x-axis, that will be the AD and that will be the V1 cos alpha. That is VW1 is equals to AD is equals to V1 cos alpha. Similarly, the VR2 cos phi will be therein. Okay, so those assumptions we are having, that is a VW2 will be a V2 cos, VR2 will be the cos phi, and for VW2, that is a VW2 will be the component of this V2 along the x-axis, that is AD, and that AD will be V2 cos of the beta. So along with those assumptions, now we are going to find out that tangential force which is going to produce the torque and which is going to have a rotation to the plate. So now we will go for one by one. So by impulse momentum principle, that is a linear impulse momentum principle, as when the jet is going to strike the plate, there is a change in the momentum, there is a change in the velocity, we can say, mass is constant, so momentum is going to change. So we are going to apply the linear impulse momentum principle because the force is a linear, that is a tangential force, we can say. So by principle, the force into time is a change in momentum, momentum is a mass into velocity, force will be the tangential force. So the force is equals to initial momentum minus final momentum per unit time, that is taking the mass as a common. So initial momentum is a mass into initial velocity and final moment is a mass into final velocity. So mass as a common, mass of the water striking the vane per second into initial velocity with which the jet strikes in the tangential direction of the wheel or the vane, minus the final velocity with which the jet leaves in the tangential direction from the wheel or the vane. It means that we have to consider the tangential velocities herein for finding the tangential force. So the mass converting in terms of the density and the volume per second as a discharge. So volume, density of the volume per second striking the vane into V1 cos alpha, that is the component of the velocity V1 along the x-axis or tangential V1 cos alpha, minus V2 cos beta. Minus here we have considered herein because it is leaving in the opposite direction or leaving towards in the negative direction of the x-axis, and it is acting in the positive direction of x-axis. So V1 cos alpha, tangential component of initial velocity, and V2 cos alpha, tangential component of the outgoing velocity. So after rearranging the terms, we will have minus of minus as a plus. So F is equals to rho A into V1, that is the area into velocity, that is the velocity of the jet striking the plate, that is a V1 into VW1 plus VW2. As field is rotating with angular velocity omega, so torque is imparting the angular velocity to it. As torque is a force into radius, that is tangential force, we can say, which we have derived herein, putting its magnitude from the above step. So we will have a torque is equals to rho A V1 VW1 plus VW2, this magnitude, into the radius. So VW1 will have the radius as a R1 and VW2 will have the radius as a R2. Multiplying them, so we will get the torque tau herein. So now for work done per second by the jet on the vane of a wheel is nothing but the force into velocity, that is work done is nothing but the force into velocity. Here the work done is in the rotation, so the force will be the tangential force, that is a torque, and the velocity will be the angular velocity. That to be per second we have considered. It means that a torque into angular displacement per unit time. So per unit time angular displacement is angular velocity. So multiplying the same, that is a rho A V1 into VW1 R1 plus VW2 R2 into omega, taking omega inside the same. So it will be now multiplying inside the bracket, so R1 omega into R2 omega. As we are knowing that the linear velocity is the product of radius and angular velocity, that is in general phi is equals to R omega. Here phi is the tangential, here instead of the phi, that is the tangential velocity will be the tangential velocity of the plate or the vane, we can say, or the wheel, we can say. So instead of the phi there will be the u, so u will be equals to R omega, and as R1 omega is there, it means that u1, and R2 omega means that u2. This is applicable only when the beta is acute angle. So when the beta is obtuse angle, in that case Vw2 or the component of this velocity will be the towards the right hand side, and it will have the magnitude as a negative. And when beta will be 90 degree, in that case Vw2 will be directly 0, okay, and directly V2 will be directing along the Vf2, that is in the leaving outside the jet in the upward direction. So in general we can write, or for the firstly for the beta 90 degree, Vw2 0 means we will have the only this term, that is rho a V1 Vw1 U1, and in generally the effects can be written as rho a V1 Vw1 U1 plus minus Vw2 U2. So plus minus we have considered for consideration of the acute and obtuse angle, and when will be the beta will be 90 degree, in that case Vw2 will be the 0. So now if you want to have the efficiency of the jet, it will be required to have in terms of the turbines and all those things. So efficiency of the jet when striking the number of the plates, those are mounted over the wheel, then we are knowing that the efficiency of the jet will be the work done per second by the jet on the vane of the wheel upon the kinetic energy of the jet. That is how much work done is actually did by the jet to upon the velocity with which jet was striking. That is it's a kinetic energy. So putting the magnitude work done per second, we are knowing that is this one, and kinetic energy is a 1/2 m into v square, that is a v1 square we can say. So 1/2 m into v1 square. So mass we are converting into the in terms of the density and volume. So density into volume, we are going per second. So volume per second is again discharge, and discharge is again area into velocity. So 1/2 rho a v1 square into v1, it will be now 1/2 rho a v1 cube. Cancelling common terms, that is a rho a v1, one of the v1. So we'll get 2 times Vw1 U1 plus minus Vw2 U2 by v1 square. So this is the efficiency of the jet we can say. So this is about the work done and the efficiency of the jet striking the number of the plates or the vanes, those are mounted over a wheel in a series. So this is the mechanism I had shown herein. So thank you very much.